Hello, welcome to Tolleson Physics. So what we're going to do today is we're going to focus on projectiles. Now we're going to look at a special limiting case where that projectile is being shot horizontally, so parallel to level ground. And so that actually makes our problem solving a little bit easier. So let's take a look at a situation where let's create a hill and let's put a cannon on top of that hill. And what we're going to do is we're going to shoot out a cannon, out of the cannon, a cannonball. All right, so let's just make up this initial velocity. Let's say the initial velocity is, I don't know, 20 meters per second. Okay, and let's say, let's put a little dotted line to my level ground. Let's say it's a big hill. So, yeah, a huge hill. So let's make it a 30-meter hill. So that's, that's about 100 feet tall. So now what we're going to do is we're going to look at what happens to this ball when we shoot it out of the cannon. And so we know it's going to drop to the ground somewhere, and it's going to hit the ground at some point. So that's actually something that we could figure out. So from the point that it comes out, so it's right about there, right, to where it lands. And so we could see what the change in position is in that particular case. So why don't we try to solve something like that? Now, the thing to remember about a projectile is you can look at it as moving in the horizontal direction and moving in the vertical direction. Why is that important? Well, when we think about the force diagram for the ball, which I'll just draw right over here, the force diagram is one force. It's just the force due to gravity, because we're going to make the assumption that the air doesn't matter. All right, so it gets more complex if the air did matter, but we're going to make that assumption in this particular case. So in certain circumstances, it's actually not a bad assumption. In other circumstances, you definitely would need to know what's going on with the air. But since the force, the net force on the ball, is only in the downward direction, acceleration only occurs in the downward direction. And so what's the nice thing about this? So this initial velocity is 20 meters. Well, that's in the x direction. So actually, let me add an x to that. And so what do we know about the y direction? Well, the initial velocity in the y direction is 0, which kind of makes things a lot easier. It makes it look like in the y direction, just like I'm dropping a ball. And in the horizontal direction, well, the ball's going sideways. And those are two independent things. And so what I can do is I can actually write equations of motion in each direction. So what am I talking about there? Well, a general equation of motion that deals with acceleration, and I'm going to use y, because I'm talking about the vertical direction, equals 1/2 at squared plus v naught x plus, t plus x naught. All right, and in this particular case, v naught is 0, and I'm going to call my starting position, so I should actually draw that on my diagram. I like to do this. Some people like up to always be positive, down to be negative. Well, what I'm going to do instead is right here, that's my 0 position, and going downward is positive. And the reason I do that is, well, the acceleration due to Earth's gravity is in that direction, and the direction the ball's moving is in that direction. I don't have to deal with any negative signs, which makes life a lot easier. And so what does this equation actually become? Well, this a, we actually know what a is. It's the acceleration due to Earth's gravity. So I'm going to change that to a g. So here is what's going on in the vertical direction when I'm starting with a initial velocity of 0 in the y direction. What about the x direction? The x direction is completely dependent upon it moving at a constant velocity because there is no forces in that direction. And so I can go back to my definition of a velocity, and this is the cross-multiplied version of that I have the velocity in the x direction times time tells me where it is, and I'm establishing my x equals 0 at where the ball starts. And so I can actually take these two equations, and the thing that links these two equations is time. And so I can take these two equations and ultimately solve for x. All right, so how am I going to do that? Well, I can substitute this either way that I want. I could solve this for t, shove it into there. I could solve that for t and shove it into there. Since I want to know x, I guess I'll do it the other way. And so what does that mean? I got to cross multiply. I get 2y over g equals t squared. So t equals the square root of 2y. And I apologize, my y's and g's look similar. And so then I can put that into this equation. So now x equals v naught x and this good stuff. So 2y over g. All right, and so then, so this is a general expression that I derived from my basic equations of kinematics that we learned in Unit 1. And so now I could go ahead and actually solve this. So where's it going to hit the ground? Well, x equals, what did it say, 20 meters per second. I said it's 30 meters off of the ground. And let's just go ahead and use 10 for the acceleration of Earth's gravity. So what do we get? 2 times 30 is 60 divided. So then I would have this square root of 6, and that's meters. Is that right? No, meters cancel, and divided by nope, seconds squared. Okay, not doing my unit analysis correct. There we go. And so then off of the top of my head, I need to grab my calculator. The square root of 6 is one I don't actually have memorized. So square root of 6 is 2.45, and then I multiply that by 20. And so that'll hit the ground pretty close to 49 meters away. All right, so it's going to hit the ground 49 meters away. Now, I could have done this step by step as well, because what if I wanted to know how long it was in the air for? Well, I could have just gone from this equation right here. In case I did something wrong here, why not use that equation? And I've actually solved for t down here already. So let's just plug right. So t equals square root of 2y over g. So t equals 2. What's y? It's 30. What's g? It's 10. And so that's what this is, right? So that's actually time equals the square root of 6 seconds squared, which equals, what did I say, 2.44 seconds is how long it would be in the air for. And realize how long it's in the air for, at least is based upon what's happening in the vertical direction only. It doesn't care about the horizontal direction. All right, so the key thing to remember when looking at different type of projectiles is you can treat the vertical and the horizontal completely separate from each other.